Have you ever pondered about the necessity of well-structured data in the world of technology? Picture this: a world where data is scattered, without structure or relation, like a jigsaw puzzle with all its pieces mixed up. It's hardly imaginable, isn't it? This is where data design steps in, acting as the guiding hand that sorts and organizes this jumbled data into a coherent and meaningful structure. Data design, or database design, is crucial in ensuring data integrity, consistency, and accessibility. It's like the architect of a database system, defining its structure and organization. The implications of data design are far-reaching, impacting sectors from healthcare to finance, from social media to transportation. It shapes our decision-making processes, from simple choices like picking a restaurant based on reviews, to complex ones like predicting market trends for strategic investments. In this video, we'll delve into the key aspects of data design. The journey of data design commences with understanding and analyzing the data requirements. Picture yourself as a detective, piecing together a complex puzzle. The first piece? Identifying the types of data the system or application will store. This could be anything from customer details for a retail app to weather data for climate research. Next, we dive into the relationships between these types of data. How do they interact? What are the dependencies? Understanding these relationships is crucial to designing an efficient database schema. Then we must consider the constraints. These are the rules that the data must adhere to. For instance, in a school database, a student must be enrolled in at least one course. Lastly, we examine the access patterns. How will the data be retrieved and manipulated? Will users need to access a single data point or aggregate data across multiple points? A thorough data requirements analysis lays the foundation for effective data design. Once we have a clear understanding of the data requirements, we can start with conceptual and logical data modeling. In the realm of data design, conceptual data modeling is our first port of call. Its purpose? To identify the high-level entities, attributes, and relationships within our system. Think of it as drawing the blueprint of a building, where we outline the rooms, corridors, and connections, but without specifying the materials, colors, or finishes. For this, we predominantly use techniques like entity relationship modeling, also known as modeling. This method of conceptual data modeling allows us to represent the conceptual structure of the data, irrespective of any specific database technology. It's like creating a universal language that can be understood by different database systems. So we've identified our high-level entities, attributes, and relationships. Now what? It's time to transition into logical data modeling. Logical data modeling is where we transform our conceptual data model into a more detailed representation. This is akin to choosing the materials for our building, deciding on the colors, and determining the finishes. We're now considering the practical aspects of our design. In this phase, we're defining the logical structure of the data. This involves specifying tables, columns, keys, and relationships. It's like creating a more detailed blueprint of our building, marking out where the light switches go, where the plug points are, and how the rooms are connected. To do this, we use techniques such as relational modeling. This method helps us translate our conceptual understanding into a logical structure that accounts for database implementation considerations. It's a crucial step as it prepares our data for the real-world application. These modeling techniques help to define the logical structure of the data, setting the stage for the next step. So just as an architect wouldn't start building without a detailed blueprint, we shouldn't start building our database without a comprehensive logical data model. It's the key to ensuring that our data is organized, accessible, and ready to serve its purpose efficiently and effectively. Now, let's get into the nitty-gritty of normalization and denormalization. In the realm of data design, normalization is the proverbial knight in shining armor, keeping redundancy at bay and preserving the integrity of your data. Picture it as the process of simplifying complex data structures, breaking down larger tables into smaller, more manageable entities. This isn't just about organization for organization's sake. It's about eliminating potential anomalies that can occur when you add, delete, or update data, thus ensuring a smoother, more efficient database operation. But the story doesn't end with normalization. Enter denormalization, the strategic counterpart to normalization. While normalization focuses on reducing redundancy, denormalization embraces it. Seems counterintuitive, doesn't it? But there's method in the madness. Imagine a read-heavy workload, where queries are frequent and performance is paramount. Here, denormalization comes into play, intentionally introducing redundancy to improve performance or simplify query processing. It's like a shortcut, allowing stored data to be accessed more quickly and efficiently. However, this convenience comes with a caveat, a potential increase in the storage space required. Denormalization might involve storing redundant data or pre-computing aggregated values. This way, rather than having to compute these values each time a query is made, the pre-computed values can be retrieved, saving precious time and computational resources. With these processes, it's all about balance. Normalization and denormalization are not opposing forces, but rather two sides of the same coin. They work in tandem, each playing their part to strike the right equilibrium between efficiency and performance in a database. Normalization ensures that your data is well structured and free from anomalies, laying a solid foundation for your database. On the other hand, denormalization optimizes your database for specific workloads, often improving performance where it's most needed. So whether you're dealing with a write-heavy workload where data integrity is key, or a read-heavy workload where speed is the name of the game, the choice between normalization and denormalization can be instrumental in tailoring your database to meet your specific needs. These processes balance efficiency and performance in a database, tailoring it to specific workload needs. With the logical structure in place, we move on to physical data modeling and data integrity constraints. Physical data modeling is the stage where we roll up our sleeves and get hands-on with the Database Management System, or DBMS. Here we map the logical data model to the physical storage structures supported by the DBMS. The aim is to ensure that the data storage is not only efficient, but also effective in meeting the system's requirements. We define the physical implementation details, such as storage formats, indexing strategies, partitioning schemes, and optimization settings. These decisions are crucial as they directly impact the system's performance and responsiveness. Now you may wonder, what if the data changes over time? That's where data integrity constraints come into play. These are the rules and relationships we enforce within the database to maintain data consistency and accuracy. For instance, primary key constraints ensure that each record within a table is unique. Foreign key constraints, on the other hand, secure the relationship between different tables, preventing any discrepancies. Then we have unique constraints that ensure that all values in a column are distinct, preventing any duplication. Lastly, there are check constraints that validate the values based on a specific condition. These constraints are like the guardians of your database. They ensure that the data stays reliable and accurate, regardless of how it's accessed or manipulated. In essence, physical data modeling is like building the foundation of a house, while data integrity constraints are the safety measures that keep the house standing tall. Both are vital for the system's overall health and performance. They ensure that the data stays consistent and trustworthy, providing a solid base for the applications that rely on this data. In the end, remember that data design is a dynamic process. It evolves with the needs of the system and the users. Therefore, always keep your data design flexible, scalable, and adaptable to change. These steps ensure that the data stays reliable and accurate, regardless of how it's accessed or manipulated. Finally, we need to consider data access patterns in our data design. This is no small detail. It's about understanding how our data will be accessed, queried, and manipulated by applications and users. It's a bit like predicting the future, anticipating the needs of those who will interact with our database. Let's think about a library. A good librarian knows which books are most often checked out and places them within easy reach. Similarly, in data design, we optimize our database schema and indexing strategies based on common access patterns and query requirements. If we know a certain table in our database is frequently accessed, we might choose to index it, making it faster to query. Or if we know that certain data is often accessed together, we might store them in the same table or partition. Understanding data access patterns enables us to create a database that is efficient, user-friendly, and responsive. So we've covered quite a bit about data design, haven't we? We started with data requirements analysis, which sets the foundation for the entire process by defining what data needs to be stored and how it will be used. We then moved on to conceptual data modeling, which provides a high-level view of data entities and their relationships, followed by logical data modeling that translates this into a more detailed and implementable structure. We also discussed normalization and denormalization, two techniques for organizing data to balance between data integrity and performance. Physical data modeling was our next stop, where we learned about the mapping of logical models to physical storage structures. And let's not forget data integrity constraints, the safeguards to maintain data consistency and accuracy. And finally, we explored data access patterns that help optimize how data is retrieved and manipulated. Remember, effective data design is the backbone of any robust database system. It impacts everything from data integrity to the overall performance of your applications. So ensure you give it the attention it deserves.